Okay, good morning, everyone. So last week we have already discussed the basic for the materials introduction for the semiconductor device. So we introduced single element species materials, especially the silicon is most important for us. And also we introduced compound semiconductors that need to combine the two different elements. For example, the element in the group 3 and the group 5. So we combine together that we can have the semiconductors that are called the compound semiconductor. And then to consider the properties, material properties for one particular kind of semiconductor, we often use a band gap as a pretty important material properties. So for example, silicon has a band gap for 1.1 electron volt, and for any material who has larger than silicon, we can consider as a wide band gap, and any material who has a lower smaller band gap compared to silicon, we consider as a narrow band gap material. So anyhow, the different band gap also indicate that this material will exhibit a different kind of a material, especially exhibited a different kind of the carrier concentration and also the leakage current. And last week we also mentioned about the basic for the crystal analysis, and then we talk about the several very fundamental structure for the crystal. For example, the face central cubic, the body central cubic. And now today we will start to talk about how we can have the proper definition for the one particular plane that we are interested in. For example, this is a typical crystal structure, but how do we define a name for this particular plane? How do we define the name for this particular plane? And how do we have the certain definition for this particular plane? So we can use a specific way to name these planes that we call as a Miller index. And the Miller index, the definition for Miller index is very simple, and then it didn't really involve a very complicated mathematics, just a certain very good idea, and that can be very straightforward to understand. So let's look at that, how actually we can start to calculate the Miller index. So in general, the Miller index, the purpose for Miller index is to describe the latest directions at plane. So like I say in last slide, we were curious at how to find a way to indicate in the particular directions or particular planes in a certain crystal structure. So therefore we propose the early time researcher proposed this Miller index. And then the procedure to calculate Miller index is also very simple. The first day is we consider the intercept in the x, y, and z axis. So for example, considering this kind of the coordination system, and we are curious about how do we make the Miller index for this particular plane. So the first day is we have to estimate, we have to calculate the intercept in the x, y, and z axis. So here is the x axis, here is the y axis, here is the z axis here. So therefore, first one we are try to estimate the intercept for this plane on each axis. For example, in the x axis, which will be equal to 3. In the y-axis, which will be equal to 2. And then in the z-axis, which will be equal to 1. So that's very simple calculation. So therefore, we can get the 3 to 1 as an intercept in the x and y and z axis. Then what we have to do for the next is we do the reciprocal of the intercepts. We do the reciprocal of the intercepts and multiply by the lowest common denominator. So what does this mean? For the text, sometimes it's a little bit confused, but the calculation is very simple. What does mean the reciprocal? That just means that we do the 1/3, 1/2, and 1/1. So that's a reciprocal for each intercept in the x, y, and z axis. But for sure that we were interested in the pretty pure integral number. So therefore we times the lowest common denominator, which will be the 6. Then we can get the 2, 3, 6. And therefore, these 2, 3, 6 will refer to a general plan indicating here. So that's a Miller index for this particular plan, which we can have the name for this plan that we call the 2, 3, 6 here. So by using this way, we will refer to a general plan as a HK, which is 3 different numbers along the x, y, and z intercepts. Especially it's a reciprocal of the intercept, and then we can get this the Miller index. So the calculation here is very simple. So let's look at some advanced case that probably you will get more sense that why we have to time to use intercept, because some of the case that we really need to use intercept, otherwise we won't get any reasonable numbers. So these are the two very advanced cases. One is, how about if we can consider there's a negative intercept? So for example, in this case, as you can see here, in the x-axis, we have the intercept of the 2. In the y-axis, we have intercept of the 3. And then for the case along the z-axis, we have the intercept of a -2. So let's do the one by one to see how we can get it as a Miller index. So as usual, we first to do the reciprocal. So we will get it 1/2, 1/3, and 1/-2. So that's a reciprocal for the intercepts along the x, y, and z axis. And next, still the same. We do the multiply by the lowest common denominator, which in the end, the result will be equal to, we times the 6, so we got the 3, 2, -3. But in the Miller index, we don't allow to use a negative symbol. So therefore, in the end, we will transform this -3 become the 3 with a hat here. So that means that in the future, if we found out that there's a Miller index with a hat on top of the certain numbers, certain intercept, that means that this is indicate as a negative direction in that axis. In here, it's a negative direction along the z axis here. So that's some particular case, but it's very often we will see the negative intercept along the particular axis. And then the next one is also we will very often to see is that liquid B has an intercept at approach the infinite. So for example, in this right hand side case, so we have the x-intercept as a 2. We have a y-intercept as a 3. But now, along the z-axis, this is the plane that in parallel with our z-axis. So therefore, this will approach to the infinite. Therefore, we also need to figure out how to use the Miller index that we can define this plane that parallel in the certain no matter for x, y, or z axis. So still, we can write it down as an intercept, which is 2 in the axis, 3 in the y, and then the infinite along the z. And then we do the reciprocal. So therefore, we have 1/2, 1/3, and 1/the infinity here. So therefore, in the end, we can gather the result of the 3, 2, 0 here. So the Miller index for this particular plane is become as a 3, 2, and 0. So now, probably you can start to figure out that as long as there's a 0 in the certain Miller index, that means that there's a parallel. This is plane is parallel in certain with a certain axis here. So that's also the reason why we have to take into account as one reciprocal intercept. That's why we have to do the 1/, of our intercept, because we have to take into account that there's a chance that we will have the plane that will be parallel with one of the x or y or z axis. But anyhow, I think here it's still very simple. You just need a high school mathematics, and then the definition is very easy to calculate it. And some more for the Miller index, that can be the certain variance for this Miller index, but still the calculation is the same, but the only change is how we can use this different bracket. So for example, like say, if we have a negative intercept in the x-axis, so we'll put the hat here. We will put as a hat on top of the 1. So we'll put a hat on top of the 1 here. So that's indicates a negative intercept. But how about for the case, for example, if we consider to use this kind of the bracket, that means this represents a family of a plane. So it's not only one particular plane, it's actually the family of planes, all the combination of a 1, 0, 0, which is combined as shown me here. 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0. And also this one is a negative in the y-axis, and this one is a negative in the z-axis. So that's a meaning of this bracket. And also, if we consider this kind of a bracket, as shown here, so this represents directions. So, for example, in this particular plane, we have the Miller index of 1, 0, 0. But if we want to identify the direction of the plane, the direction means this is the arrows that are perpendicular to this plane, so which will be these directions. So in this case, we have to denote it as this kind of a bracket. And that means the direction of this plane. And similarly, we can have this one as a 1, 1, 0. And therefore, we will have the direction of this plane. Direction of this plane can be 1, 1, 0. Just a different kind of bracket. And also we have this plane for 1, 1, 1. And then the same, similarly, we have these directions, which is a 1, 1, 1. So that's all, still very simple. And also, we can have this bracket, this kind of bracket represents a family of directions. So that's combined all the directions, which is the same like this one, but now we change to this kind of a bracket, because this bracket indicate as a direction. So that's some more definition, useful knowledge for these Miller indices. Okay, so now we move to some more very fundamental to understand that how the two different atoms how can form the bonding. Actually, this should be some knowledge that you have learned from the general chemistry. In the general chemistry or general material science, you probably have been known that there's several ways to form the bonding. So we have first one is ionic bonding. We also have the covalent bonding. We have the metallic bonding and the van der Waals bonding. So in this case, we just quickly go through some of these fundamentals. So we won't go to detail. If you have any question, I believe you can find a lot of basic information in the more generic subjects here. So but still go through the text together. So ionic bonding means this is a type of chemical bond that involves the electrostatic attraction between the opposite charged ions. In a crystal, the negative charged ions tend to be surrounded by the positive charged ions, and the positively charged ions tend to be surrounded by negatively charged ions. So a period array of atoms is formed to create the lattice. So that's all. So that's all for you have to understand for the ionic bonding. And next one, which is getting more important for us, is what we call the covalent bonding. So the covalent bonding results in electrons being shared between atoms. So therefore, so that in effect the valence energy share of each atom is full. So the idea is that if we consider the one silicon atom, as you know that the outer shell of the silicon atom has 4 electrons. If you are not aware of why there are 4 electrons in the outer shell of silicon, then you should go back to check the general chemistry. I think the general chemistry, this kind of subject should explain this very clearly. But anyhow, just assume that you guys already aware of that. So there's 4 electrons in the silicon in the outer shells, and also if you consider another silicon, we have also the 4 electrons. And once these 2 silicon is nearby with each other, and then each one will contribute 1 electron. So once we have 2 electrons that can, and then these silicon atoms share these electrons between the two atoms. So that's we call, then we can form this kind of bonding, and this bonding is what we call the covalent bonding. So again, we can foresee that how this silicon can be formed with another silicon inside the crystal, because they share the electron together, and that's because they create this kind of a covalent bonding. So that's something like for the silicon, it's very often seen in the silicon crystal. And for sure that we have some more. For example, we have metallic bonding. This is, think of the positive metallic ion as being surrounded by a sea of a negative electron, and the solid being held together by the electrostatic force. And we also have this van der Waals bond. It's caused by correlation in the fluctuating polarization of the nearby particles. It's mainly due to the polarization due to the nearby particle. But with these causes in the very general semiconductor physics device, we mainly talk about considering the covalent bonding, because that's most often seen in the most of the silicon-based semiconductor material. Since we start to talk about the crystal, we talk about the lattice plan. So now we have also introduced some imperfections and then impurity in the lattice plan that we often see. And then therefore there's two different. The first one is we call as imperfections, and the second one is we call as impurities here. So first one, so what is the imperfections? So for example, the vacancy can be considered as an imperfection. So what is vacancy? So vacancy is in the real crystal, an atom might be missing from a particular lattice site. So considering that this is a single crystal lattice, that we have lots of the atoms here, and unfortunately due to unknown somehow reason, there is a missing in this place. There's an atom missing here. The atom missing here will become as a problem for this the lattice plan, and then we consider this the missing atom place is what we call the vacancy. So like in this case, we might have this so this is a typical lattice plan that we have these atoms sitting on the one particular place. And now, if there's one atom missing, and this place is that we call as a vacancy. So this is a vacancy. And this vacancy in the end will create lots of the issue, especially related to the reliability. Because of ideally you have the atoms just nice place in this region, but suddenly you have one vacancy here. So the vacancy not only can be used in the semiconductor, can be used in the lots of daily life English conversation. For example, the vacancy in the bus, that means that you are looking for some empty seat in the bus. That's also we call the vacancy. If you try to look at the job, you also try to ask some hiring manager, do you have any the job vacancy? That also means that you are looking, try to check with them that where any available position for the job. So that also can be used as a vacancy. So in anyhow, this vacancy means that this is an empty place. This is the place that available for something else, which means that if you consider as one electrons try to flow to the left, to the right. And these electrons might start to be located in this vacancy, because the vacancy, there's no any charges layer, there's no atoms layer, and then it's available for any kind of the carrier. So the electron once flow from left to the right, so this electron might be start to being located in this vacancy. And in this case, we consider the vacancy can be something we generally call as a trapping. So this vacancy can be considered as a trapping site or trapping location. But we consider this would be the trapping issues here. So because right now you have an additional negative charge located in this empty available region, and then this creates a negative charge inside here. So in the equilibrium electrostatic potential consideration, once you have additional negative charge inside, this will destroy the equilibrium potential. So that will be cause a certain additional charge will leading to the influence of the electrical characteristic. And this is one issue. Another particular issue is that because the charge is not stable, so sometimes these electrons will be stayed in this location. That's generally we call the trapping, will be trapped in this location. But you don't know when this charge will be leak away, when this charge will be leaving this place. And once this electron trap leaving this place is what we call the detrapping. So in reality, the electron can be certainly trapping in this vacancy. And after 5 minutes, 10 minutes, 1 hour, 10 hours, 5 days, 1 year, and suddenly these trapping electrons start to leave this vacancy, and this phenomenon we call the detrapping. But in general, this becomes the issue because you cannot predict this electron when will be trapping in this vacancy. You cannot predict electrons when being detrapping. It's all related to the time issues, because sometimes the trapping might be just cause 1 second, 1 millisecond, but detrapping probably sometimes cause several hours. So in the end, it becomes very unstable for our whole system, especially related to this additional charge will create additional potential. So anyhow, this becomes unstable because you don't know when this electron be trapped by this vacancy. You don't know when the trapping electron will leave this vacancy. So that's become as an unstable state. And that's the reason we need to study the reliability. Because anyhow, this causes a reliability issue. Because as being an engineer like us, what we actually want to do is we want to precisely to estimate the device physics, to understand the physics, understand the device operation, and then to understand when the device can turn on and turn off. But once we have this vacancy, everything's become unstable because we don't know the influence of electron additional charge, and then we don't know when will happen and when will stop. So that will cause a reliability issue. So that's why the vacancy in general just create a lot of reliability issue. In this class, we won't talk too much reliability, but in my another class, I talk a lot of reliability. So the fundamental reason leading to the electrical reliability issue is lots of times coming from these materials imperfection due to the vacancy or due to these additional defects. So another one show me this one is another very often seen case is what we call the interstitials. So the interstitial is this is original atoms, but suddenly there's additional atoms placed in the region that should not have any atoms. So that's we call the interstitials. So that's also creates a certain problem for our materials, in the end cause electrical reliability issues. And also another one very famous, if you are coming from the material science in the undergraduate, you should already knew about this. This is a line defect. So the line defect is mainly considered that, for example, in this case, this is one particular crystal plane with a certain crystal arrangement, but suddenly, because of growing another material, and there's a difference in the lattice arrangement, and therefore suddenly you will see there's a missing here, and that's we call the line defect. This is a general issue we call as a line defect. So, line defect occurs when entire row of atom is missing from its normal lattice side. So you see there's a certain atom missing in this place. That's we call as a line defect. And what can be the case that we can cause this line defect? This is very often to see in the case that we try to put one semiconductor material on top of another semiconductor material. That's a previous case we call as a heterostructure. For example, one of the famous case is if we want to consider the bottom as a silicon, as a material. Now we try to grow another material on silicon. For example, the compound semiconductor, the 3-5 semiconductor, the gallium nitride semiconductor. So if we try to grow the gallium nitride on top of silicon, so you can imagine that there are so many differences in silicon. There's a band gap difference. There's a atoms lattice arrangement difference. There's so many aspects difference between the GaN and silicon. So therefore, in this interface, it's very often seen we will start to form the line defect because you try to put the two different materials together, and then they have the different lattice arrangement, lattice constant, and so on and so on. So therefore, we very often to see this line defect. This is one of example. For sure, it's not only limited for the GaN on silicon. It can be any two different materials trying to grow together. It's always possible to cause these line defects. Okay, so one more. This is something that I just did not mention, the interstitials. So interstitial by definition is an atom might be located in between the lattice sides. So there's additional atoms located in the two typical lattice place. So that's what we call as interstitials. So that's three most often seen problem imperfections that we see in the semiconductor material. Also, there's another one called the impurity. Still the same. In anyhow, no matter for the imperfection, impurity, we just consider that there's some additional atoms come in, charges come in, or some of them missing in our original lattice size here. So the impurity atoms might be located at the normal lattice site, in which cause that we consider as substitutional. So that means this is additional atom, unknown atom, but located in a regular normal lattice plates. That's we call the substitutional. And also we have this one. Imperial atoms might also be located between normal side, but they are called as an interstitial. Impurity. Of course, I think at the moment these terms are pretty confused for everyone, but it's fine. Just a pure definition. It's just if you forget it, just come back to look at. It's just not that lots of the very critical for the first certain semiconductor physics and device understanding, but it's crucial that you should be aware of that our material, semiconductor material, is not always perfect. And if there's no perfect, we will have additional charge, and this additional charge will cause a lot of the instability for our device. Okay, so the last slide that I would like to show in here before we conclude this chapter is that what we have learned from this chapter is mainly for the basic materials properties, and what I think the most important is Miller index, that how we can try to define the certain plan. And this just want to show you that with your certain understanding now, probably you don't believe it, but if you try to look at this paper, you probably can sense that some of the term is just exactly what we are teaching in this chapter. It's just a chapter 2, but I believe if you try to really understand from the chapter 1, chapter 2 so far, this literature, this academic paper probably is not that difficult for you, because all these critical terms we have already mentioned. So let's look at together. So this paper is what we call the performance dependence of the CMOS on a silicon substrate orientations for ultra-thin oxide nitride, hafnium oxide, gate dielectric. At least from the title, of course, some of the terms you don't know. Probably you don't know what's oxide nitride, hafnium oxide. That's fine. But there's several terms that we have already mentioned. For example, the CMOS, that's already mentioned. With considering as a NMOS plus PMOS, that's what we call the CMOS. But it's fine. We will still talk about CMOS later. But the most important for this literature is about the orientation. Most of you might feel like the Miller index sometimes just way too simple. It's not that difficult. But as you can see from this literature, still very important, because this paper is talking about orientation. But how do we define the orientation? We need to use the knowledge coming from the Miller index. So as you can see the abstract here, dependence of a CMOS performance on silicon crystal orientation of 100, 111, 110. So now you see why we have to understand the Miller index. Otherwise, you won't be understand what does it mean the 100, 111, 110. And particularly, this just where, like the 10 minutes ago, we explained what is a plan. It's a 100. What is a plan in the 111? What is a plan of 110? So that's why this paper is with the knowledge you have from this chapter, for sure that you are already probably can catch more than 50% what this paper is talking about. So let's go through the abstract together. It's not that difficult to read the paper. Sometimes we just go to the abstract. First we look at for the title for sure, and then you can just, if you look at title, you probably can get like a 30% sense of what this paper look like. So if right now we don't read the whole paper, we look at the title, we can already guess this is a paper talking about the different orientation and the different dielectric and different performance on the CMOS. And what does performance here? In most of the time, when we talk about performance, just refer to as a current. So we are curious about how the current dependencies on the different orientation And then we also consider the different dielectric, which is oxide nitride, hafnium oxide. So let's go through the abstract together. So this is a paper talk about we have been trying to consider the 3 different orientation and with a dielectric less than 3 nanometer. And first one in this paper, they mentioned the whole mobility enhancement for more than 160% for these 2 dielectric, but the most important is on this substrate, 110 surface compared to the 100. So that's why we have to use the Miller index. So this gives us an indication that what kind of surface is a 110 compared to 110. And also, because this paper is talking about the performance, so you can imagine that the structure of this paper should be, if we don't look the paper in detail, but imagine that what would be the typical logic behind to structure of this paper. It could be, first, they do something on the different surface. They found a certain improvement, and later they want to prove that there is a certain influence on the driving current. In the end, they also talk about what would be the percentage increase. So therefore, the second part, this abstract focus will be the driving current, because driving current is consistent. It's correlated with the performance mentioned in the abstract. So this abstract term will be reflect again in the title will be reflecting again in the abstract. So the CMOS driving current is nearly symmetric on this particular orientation. And also in the end, because this paper is talking about the CMOS, so therefore they also showing that this is a P MOSFET on 110 under this particular surface. So anyhow, of course, probably right now in your mind, it doesn't really quickly correlate the surface, which is 111, which is 1100, which is 110. But anyhow, this gives you a sense. It just means a certain plane considered as a Miller index. And also in this paper, this is all the paper written by the negative people, which means that all the English writing here should be very reliable, should be worth to reference, should be worth to understand how they can try to construct this academic paper. So in this course, I will also time to time to share these papers and try to link the knowledge you will learn from this class to some academic paper, some advanced knowledge you should learn. So also, this one I want to emphasize that when we write the abstract and the summary or the title, everything should be consistent. So normally when we try to write the paper, we always divide by the 3 key conclusions. So the first sentence here, this one, dependency of the CMOS until here. To be honest, if you try to read in detail, this sentence actually is just the same as a rephrasing coming from the title. The title mentioned for the CMOS orientation and then the dielectric. So the first sentence of the abstract, this can be considered as a general structure. The first sentence of abstract just typically considered as a rephrase of our title. So still the same. The keyword still exists, CMOS, orientation, dielectric, right? So if you try to read the detail for this abstract and think about this is exactly the same meaning, just like the title. There's nothing different. We just try to rephrase the title and expand a little bit. And now the typical structure for the academic writing is first we will break. We will try to give a general break in the first sentence, and that need to be rephrased coming from title. And the second, we'll start to consider finding to point out the three most important conclusions. So in this paper, there are the three most important conclusions. The first one is here. It talks about how mobility, blah, blah, and then in a certain service, and so on, so on. So that's the first conclusion. And second one, this one. So the CMOS driving current is nearly symmetric on a certain orientation. And then the last one is this one. So this is a very general academic writing that we don't, when we write the academic paper, we are not writing the novel. We are trying to be the straightforward to the point. So therefore, the first sentence is always the refresh of the title, and then later we will try to pick up the three important breakthroughs in this study and try to read it, try to write it in the abstract. Just show me here. So there's a 1, 2, 3. And then similarly, if you look at the summary, still the same. The summary of the first sentence of summary is exactly as another refresh coming from the abstract. So the electron hole mobility has been mentioned in the CMOS device fabric on silicon substrate with a different crystal orientation. So this is exactly the same like the first sentence abstract. But in the summary, we will also emphasize again the conclusion. So still, we will list the three conclusions. So if you try to look at this sentence, this is exactly like the abstract, but just use a different way to rewrite it. But the message that the summary want to deliver is very similar to the message coming from the abstract. So if you follow this academic writing style, at least you start, finish, you complete the abstract, you complete the summary, and then between the abstract and summary, just lots of result discussion, try to support your findings, support your conclusion. So if you look at this paper in detail, for sure there are many papers, there are many figures, but I only list this one. So this is one of the key figures. So I won't explain in detail, just let you know that the y-axis is a whole mobility, but since I want to emphasize is this one, 1, 1, 1, and also this one. So now you see, this is an academic paper. They use Miller index that we just learned. They use two different Miller index indicate as a plane and directions. And also this is electron mobility. They also use a different Miller index because this is indicate that the dielectric in the different orientation in the end cause a different mobility. But why they care about mobility? Because in the end mobility is correlated with current. So you feel our current is certainly proportional to our mobility. So as long as the mobility high, we always got the high current. So that's the certain important information that from this academic paper, but with the knowledge you have right now, that's enough for the analysis. Okay, so let's move on to the last one. The main takeaway for this chapter is we are talking about semiconductor materials and crystal. So we talk about the elemental material, silicon, germanium, and there's a certain compound which is combined two different material. And also we talk about the material that has a large band gap compared to silicon. Sometimes we call it a wide band gap. And then the band gap will determine the electrical, optical, and then the thermal performance. And when we talk about how we can actually form the device, so device is actually the formation just considered as materials plus the junction. So the device are mainly considered once we have a materials, and then we try to put together that will form the junction, and then will lead to the overall influence on the device characteristic. So the device are built from the different junction engineering. So we have the metal semiconductor junction that will form the Schottky ohmic contact. We have the PN junction that will form the diode bipolar junction transistor. And the thyristor we won't talk about in this class, but just for your information that as you already knew, diode is like this one. We have a P and N, that's a diode. And now we put a little bit complicated, like here. We have a PNP, two back-to-back diode. This one can be considered as a this one is considered as a, not can be, as a transistor we call the BJT. But furthermore, we can also have this structure. Furthermore complicated with a PN. This can be considered as a transistor as well. And this PN structure, which considers 3 different PN junctions. So we have a PN junction here, here, here. And therefore, for sure, you can imagine that physics here is more complicated. But this transistor is what we call as a thyristor. Okay, so then we have this heterojunction junction, for example, the LED or gallium nitride hand. We also have this MOS junction that consider metal oxide semiconductor, which is the very crucial for understanding of the MOSFET. And then device physics mainly governed by band theory, carrier transport, and then the Poisson equation. So these are the main key takeaway from this chapter. And also when we talk about the crystal structure for fundamentals, we talk about the several different solid. We talk about amorphous, polycrystalline, and single crystalline. We talk about the single cubic, BCC, and FCC diamond. We also talk about the silicon germanium, and most important is actually this one, Miller index. Describe the crystal plane and the directions. And also we let you know that the lots of the crystal defect, that we have the vacancy, interstitials, impurity, in the end that will strongly impact on the device behavior. Okay, so that's the end of this chapter. So we will start to move to the next one. So now we start to getting more and more complicated, especially this chapter is sounds complicated, but in the end you will figure out that actually the knowledge we needed for the semiconductor engineer is not difficult for us to understand the certain important part. But we don't have to understand everything, but the certain part that's enough for us to help us to understand, or to help us to analyze the issues that we will face. So this chapter we mainly talk about the quantum mechanics. So the idea to understand the quantum mechanics is because in the quantum mechanics that this can be the mechanism to help us to understand the device characteristic. And let's use a simple case as a MOSFET as an example. So if we consider the one structure of the MOSFET, so we have a substrate, we have a source and drain. Source, drain, and in here we normally consider this is a P-type substrate. On top P substrate we have N plus source and drain, and then on top of source drain we have the dielectric. This is our dielectric, and then on top of dielectric we have the gate. So as I already mentioned, that the typical operation for MOSFET is that normally we will ground the source. The source will be biased as a 0. And now we will start to apply the voltage from the gate side. And as I mentioned previously, we are interested in as a drain current versus gate voltage. So therefore, we are interested in the case that where we increase the gate bias, what will be the gate bias will influence our drain current. So in this case, we'll first to gradually increase the gate bias. And as I already mentioned previously, the typical characteristic for the IDVG in the MOSFET is the first one, there will be the no current, and after certain gate bias, which is larger than our threshold voltage, when this gate bias is larger enough, as you know that once we apply the positive gate bias here, for sure that we will have the negative electrons will be attracted in this region. Normally we call this region as a channel. And because of we also will apply the small drain bias here, for example the positive 1 volt here. So now you have a negative electron here, and you have also the drain bias here. So we can foresee this negative electron will try to flow from the source to the drain, right? That's an electron flow. And this electron flow will be opposite direction of the general current flow. So we will see the current ID formation in the direction toward the drain side. But because this is, but it's more straightforward to use to consider the electron, because in the most of the case we talk about the MOSFET, the electron is the main carrier to transport. So it's sometimes more easy to use the electron. But just let you know that the general current is in the opposite. The current is opposite as the electron current. So the general current is in this direction. So we consider this kind of the characteristic, so we can understand once the gate bias is larger enough, beyond a certain critical number, that's we call as a threshold voltage. So we can start to see the current increase, and this critical voltage is we call as a threshold voltage, VTH here. So that's a typical MOSFET operation. As I say that later when we talk about MOSFET, we will talk some more details. For sure that there are some more things you know, but this basis that's enough to understand the typical IDVG characteristic. But the one thing, this curve actually we have been mentioned, I think so far maybe 3 times, 5 times already. So I think everyone should be at least a little bit familiar with. But the one thing that we don't mention is that this is a 3-terminal device. We only consider drain current versus gate current. But have you ever wondered, this is the region where we apply the gate. So how about the gate current? This is something that we have never talked about. Because ideally, this is insulator, right? If you consider the insulator, so therefore, this electron should not be able to go through the insulator and become as a gated current. This electron can only change to move toward the drain side, become a drain current. But in reality, this is ideal case that the electron has no way to flow toward the top because this is an ideal perfect insulator. The perfect insulator should stop every carrier. But in reality, if you do the characterization of your semiconductor device, especially this curve, the gate current versus the gate voltage. In this case, you will never measure the zero gate current. You always see there's a current flowing. And then in the end, if your gate voltage is large enough, you even start to see there's a gate current shooting. And this something is completely contradict to a typical physics, especially the Newton physics. Because Newton physics tell us the electron here has no way to cross over this dielectric, become this lead current. So let's just try to remind you what does the Newton physics tell us. The Newton physics tell us if you consider there's a certain wall here, and then the Newton physics tells us that you try to throw a ball against this wall. There's only the one scenario happen. The balls will bounce back. There will be only the reflections. So this is a classical physics. Tell us. This is something we learned from the high school. But if you try to follow this classical physics and put in this consideration, imagine this is a ball, so it's just like our electrons. Electrons is also kind of a certain object. So in this case, you have electrons injected in this wall, which is our dielectric. The electron can be only reflection, and you won't have any chance to see the carriers in this side. So this will not going to be happen. So based on the classical physics, the gate current will be always equal to 0. And therefore, we found out that the classical physics cannot help us to understand our semiconductor device because we never see this will become 0. We see this always, and then it's getting more and more as we increase the gate bias. Therefore, we start to think about what else the physics to help us, and then the quantum mechanics help us. Again, if you consider the quantum mechanics, still the same. But now in the quantum worlds, we still have the wall, but we don't call that as a wall. We call that as a barrier. So there's the barriers. But now towards this wall, towards this barrier, we have a certain carrier here, which can be electron or hole toward this barrier. Still the same, we will see the reflection of these electrons. But the one thing's difference is that we start to see this electron hole can cross this barrier and penetrate this barrier and reach to the other side. And this we need as a quantum mechanics teach us how this can happen. And because of this penetrating phenomenon, that we can find the electron holes on the other side. And this justifies the reason why we start to see the gate current existed as a gate bias increase. And this justifies that why this current can happen. And therefore, we consider this graph into our MOSFET structure, and that will become the carrier, the electrons in the channel can start to penetrate to our gate electrode. In the end, become as our gate lead current. So that will be our gate lead current, but still the same. This arrow is electron direction, but the current direction is the opposite of electron. So the current direction will be into our device, but the electron direction will be out of gate. So that's the reason why we can say this carrier can penetrate the dielectric and reach the gate side and become leakage current. And that's why we see this kind of IGVG characteristic. And these phenomena were called as a tunneling. And this tunneling phenomenon is getting more and more important if we work on the very small scale device. If we work on the 3 nanometer dielectric, 2 nanometer dielectric, 1 nanometer dielectric, we will see the gate current is increasingly high. And that's because of very series of these tunneling effects here. So because we have to understand this, that's why we need the quantum mechanics help. That's why this chapter is all related to how we can use a fundamental quantum mechanics to understand the tunneling mechanism. In the end, becomes a certain non-ideal effect in the semiconductor device. Okay, so let's start to reach this goal. For physics point of view, it's very easy to understand, but to go through the point until this physics, there are lots of complicated equations. That's why most of the fresh student will be afraid to understand the quantum mechanics, because the equation is a little bit way too complicated. But in my class, I try to focus on the physics understanding, and then the equation, I believe you guys has been practiced for the test, for the calculation until the whole life so far. So I believe the calculation should not be difficult for everyone. Okay, let's start to go step by step to understand this chapter. The first one is, after this lecture, you will be able to understand why the quantum mechanics required to describe the electron behavior in the semiconductor. You understand why in the electron in the semiconductor we cannot use typical Newton physics, and also describe the key principle for quantum physics, including the energy quantization, wave particle duality, and uncertainty principle. To be honest, these are also not new, because I believe you have already learned this from the modern physics. That the modern physics already tells us the wave particle duality, the uncertainty principle. But the one thing's difference is that probably you don't know why we have to learn this when you follow the modern physics, because the modern physics is a general subject. When they teach you modern physics, they don't explain this for any purpose. They just explain to you that there's lots of genius scientists in the past who proposed this series, and then they prove this series really existed. For sure, this quantum physics can be used in the lots of domains. So like me, when I learn the modern physics, I just get confused that how do I use this? But now, for semiconductor, we have very clearly goal. We try to use this to analyze the semiconductor device. And also, understand the physics meaning of a wave function and probability density. Also, the concept of wave function is something you must learn from the modern physics. But at the moment, the wave function just a kind of a tool for derive a lots of equation, put the Schrodinger wave equation, derive something, but you will get lost that you don't know the goal and what's the application of wave equation. But in this class, we will talk about the application of wave equation that we can use in the semiconductor case. Yes, so Schrödinger's equation, that's something you learn this, but now we will go through again and understand the fundamental quantum phenomenon, especially the tunneling, these kind of issues. So first one, why do we need the quantum physics? Because in general, we need the quantum physics to describe the electrons. Movement in the extremely small world, which is a micro world. That's why the typical physics doesn't work, because typical physics is considered as a case in our general life. It's a pretty large scale. But if we consider very, very small, down to the micrometer, nanometer, we need a certain new physics help us. And then that's why we need to have the quantum physics. So, like say, if it is a large object, the Newton's mechanics work very well. But in the micro world, the Newton mechanics doesn't work. So now, the problem, what we are trying to understand is that we have a piece of a semiconductor material. This is our piece of a semiconductor material. What kind of material? It doesn't matter. Silicon, compound, doesn't matter. But now we are interested in if there is a carrier, for example, electron, try to flow in this semiconductor material. How do we understand the electron movement in this piece of a semiconductor material? Especially the electron is extremely small. So therefore, the problem for this electron flow in this piece of a material becomes a problem. Actually, if you try to room in the semiconductor material is a kind of the atom that combine with a periodic structure. So if you try to room in such small scale, such small scale in this semiconductor material actually is as a lots of atoms. We have atoms here, atoms here. That's how we explained in last chapter, right? So this actually material just atoms try to bonding with each other and then place in the periodic structure. So now the questions, one electron movement in the material this kind of question become as electrons moving in a place where that has a periodic structure. So now we can start to simplify, or not simplify, it's actually getting complicated, that the question is become as a electron moving in this periodic structure that has many atoms. So now we extend the original question to become as this question, that the electron moving in this periodic structure. But now imagine electron moving in this periodic structure. Sometimes these will close to these atoms. Sometimes these will far away from the atom. So therefore, you can imagine that the electron movement here is sometimes very close to the atom, start to far away the atom, nearby the atom, far away the atom, nearby atom, far away atom, and then the one thing difference is the potential. Because once the electron close to the atom, you face a one particular potential. Once electron far away from the atom, that actually will be face another potential. So in the end, this question can be considered in another aspect, is that the electron moving inside the periodic potential place. So therefore, you are very open to see in the semiconductor textbook, you have the periodic potential because this is atoms without atoms, atom without atom. So the potential is regular, periodic. So now you can rewrite the potential, redraw potential as like this one. Right, because of this potential is due to the periodic atoms. The periodic atom will create the periodic potential, and now the electron movement inside this periodic structure, it just means that this is the electron will face this periodic potential. So the electron can be sometimes in this place. The electrons can be in this place. The electrons can be in this place. So this is exactly a problem that we want to solve. So a material, let me just restate again. Electrons moving in the material can be considered as an electron moving in the one periodic structure, like here with many atoms periodically in this lattice sign. And then each atom, because this is a periodic structure, so the atom will also exhibit as a periodic potential, like here. And therefore the questions become the electron moving in the region that has this periodic potential. And now electron can be moved in this, what we call the free space, because it's pretty far away potential, or the electron can be moving in this potential well, 能量井, 电位井, that's what we call the potential well, like just this one. So that's why you will see in the later slide, we will explain the case of the electron moving in the free space or the electron moving in the potential well. Okay, so we will stop here. So for the 10 minutes, we'll come back at 11, so you get a certain time to think about this.
IGVG， 他是不是说你是说因为有这个用框程来解释这个理论？
对。
那为什么会有个螺旋跳上？
哦，那是因为它的电压够大的话，它康动力会更多。
它就是正常就是符合 V 的 I R， 可是它正常。
没有，它跟 V 的 I R 也不一样，它纯粹就是因为你的这个电压够大，它康动力机制会更多，所以你会更多看到更多电。
但是它
会有一些 bending。但是
它又会维持在一个稳定的状态。
一开始会有一点点稳定，那个是示意图，真的来说可能会慢慢往下，会 depends on 不同的 dielectric 跟构图都会有关系。
哦，
对。
然后老师你说这边是因为是有一个连接吗？
对，它就会有一个
那个横条幅那个到底是什么意思
？potential。
哦，是
对，那个是 potential 电位。
哦，
电位。
对。
OK， 好，好，但是去 TSI 是比较高。
没有申请，
哦，
他 TSI 因为像
我知道。
TSI 开一些，
我知道。OK，
有传开。
好，
名额好像才1-2个。
好，
那老师，你就是目前老师这边跟 TSI 有没有一些？
我们很多。对啊，像那个他们做前端调查，之前跟 TSI 也有蛮多的。高频其实我们在 TSI 会用到蛮多高频量测。
那所以等于说，我这个选择只是算是跟专题是很大的关系，或者就是
可以有看，但是到时候可以看看 TSI 研究员是谁啊？
没有特别写，他就只有开制作线，就是贴上来开。
到时候你如果立足的话，你可以跟我讲一下，就是那边做，我可以跟他谈谈，因为 TSI 应该大部分都。
你说如果真的有
效，对，你可以跟我谈的，你可以跟我讲那边就，我可以找研究员来看，就是说如何可以跟你，因为你现在也会帮忙做量测。
对，就是实验室为主。
对，那可以去那边，然后我们也有去那边量测。OK， 对，可以看看，我觉得有可能。高频量测这边结束，maybe 我可以帮他OK， 对，就是那边谁不能开一点。对，
他其实还有职位，只是我看稍微扫过一下，他有开的职位，我觉得这个可能是跟
我拍一下，我让我拍这个，就拍，可以传给你。好，我再问一下。
好，这边好。
今天下午开会是可以线上开。
对，那你就 set 那个
用上次的买进，就是
那个连接嘛。
对。
那个可是我那个连接是礼拜3，
所以它不能，所以还得开一个。
你可以在里面 set 连接借给我，最好是你们 set 连接借给我会比较好。我在外面 set 连接，我觉得有点难。
上次那个学长新阳用就是好像没有成功。
那是因为没有 TSMC 的 email。
对，他之前先开公司面先设，然后好像因为那个好像申请，
那可以用 Gmail 吗？可以用那个不能用 Google。那你可以问起来嘛，它里面在的跟外面开。对，因为之前我蛮多线上干部。对 ，OK， 好。 Okay, so we will start from the continue for the course, and then before we start, I think now we have finalized the registration or enrollment for this class has been finalized. So now we will take the attendance. So we will call your name. So once you hear name, please raise your hands. 邱瑶欣、钱延珍、黄仲轩、于承玉、陈蔡义安、陈宇杰、王博威、徐伟柔、邱浩伟、林柏春、张新宇、魏廷华、陈建鹏、谢怡锦、方子琪、苏子全、徐守义、李诗婷、张雨晨、黄永纯、吕怡静、陈世丹、吴敏燕、罗怡晨、黄品哲、陈思翰、林彦荣、张敏杰、林玉天、苗天瑞，苗吗？苗天瑞。钟礼任、林博瑞、郭廷维、赖佩涵、徐瑞谦、曾冠瑞、杨洋、谢文豪、刘子安、汪之允、钟毅、郑轩恩、李连恒、张文旭、曹媛媛、许浩哲、游成斌、赖静怡、王艺轩、林哲杰、王玉敏、马克俊、戴宇翔、 戴宇翔、王瑞甫、陈怡贞、杨世熙、沈婷、洪明阳、陈义胜、郭信宏、柯冠敏、杨子谦、蔡玉章、洪香宇、翁成祥、林永伦、王伟博、许宏伦、王新成、刘子睿、白诗玲、陈义松、陈柏霖、张以慧、彭志平、李怡轩、徐明杰、郭念祖、刘浩轩、林贤昌、洪曼丽、潘良文、施安博、马成辉、黄日敏、戴家全、黎黄青松、婉月端、郑博伟、张淑娜、张佑群、林玉佑、沈立普、胡荣成、邱伯君、简凤仪、杨俊伦、叶立伦、倪雅芝、王贞杰、陶氏美惠、夏安敏、宛氏明顺、石爱如、石敬伟、杨博义、江品轩、温子怡、王少奇、田子伦、陈敏杰、陈柏宇、戴伟成、陈瑜轩、林义彤、 Okay. Okay, so now we start to also brief to mention that what would be the general principles we needed for the quantum mechanics. So the first one is the principles for principle for the energy quantum. And the second one is a wave-particle duality principle. And then the last one is the uncertainty principle. So these are the three fundamental principles that we need to use these to further understand and develop the quantum mechanics. Also, some more basic modern physics will also needed. These are the pretty basic knowledge. For example, the photoelectric effects here. So this demonstrates an inconsistency between the experimental result and classical theory of light here. So according to the classical physics, if the intensity of light is large enough, the wave function of the material will be overcome and electron will be emitted from the surface independent of the incident frequency. But the observed effect is that at a constant incident intensity, the maximum kinetic energy of the photon electrons varies linearly with frequency. And with a limited frequency, V equal to V0, and below this one, which no photon electron is produced here. So based on these descriptions, we can have this figure where the x-axis is a frequency. And then the y-axis is a maximum kinetic energy. So therefore, the observed effect is that this will vary linearly with the frequency, with a limiting factor of V equal to V0. So therefore, this suggests that beyond the certain frequency, and then we start to see the linear increase with linear with frequency. So that's a photoelectric effect. And as I say, for this concept for the energy quantum here, so this is a very old, but it's a very classical concept that Planck in 1900 considered that the thermal radiation is emitted from the heated surface in the discrete packets of energy that we call this discrete packet of energy that we call the quantum. The energy of this quantum is given by E is equal to h mu, where the E is equal to hv, where V is a frequency, or h mu, this one is the frequency of radiation, and h is a constant that we call as Planck's constant. So that's a typical equation. And in the 1905, the Einstein interpreted the photoelectric result by suggesting that energy in the light wave is also contained in the discrete packet or bundles, and the party-like packet of energy is called a photon. Whose energy is also given by E is equal to hv here. So the photoelectric effect explains how the discrete nature of photon and demonstrate the party-like behavior of photon, and the mass kinetic energy can be expressed by here. So in this is all other fundamentals relating to the modern physics. So this is not the goal for that we should lecture in this class. For any things that you don't fully understand, I suggest just look at some more basic textbook or online material. I believe that they have explained better. But this one we just quick overview that what we have been known for certain basic principle, but we will base on this basic principle to further develop that we need for the quantum mechanics. And also another one that well known that you should already knew is about the wave particle duality, because the photons X both wave and particle. But how about for the electrons? So we have these competent effects that demonstrate the party-like behavior of an electromagnetic. So in the 1924, the Du Bois assumed that the existing of a matter wave. He suggests that since a wave exhibits party-like behavior, particles should be expected to show wave-like property. The hypothesis of this Du Bois was the existing of the wave-particle duality. So based on this wave particle duality, so we can get this equation that the wavelength of the particle can be expressed by this equation. Also, these are also very well known, the uncertainties principle. So the Heisenberg uncertainty principle given in 1927 also applied primarily to very small particles and states that we cannot describe. With absolute accuracy behavior of these subatomic particles. The uncertainty principle describes a fundamental relation between the variables, including the position, momentum, and also energy and time. And therefore, we have these two well-known uncertainty principle, which is this one. The momentum times the position is larger than h bar. And also, the energy times the time is also larger than h bar. So that's the uncertainty principle. So if you're not really familiar with that, just go back to check some modern physics textbook. They can explain better. In here, we just briefly go through these because these are the fundamentals, And once we have this fundamental principle, we start to will deal with the real problem that we are interested in. So, as I say, that when we consider as electrons movement in a semiconductor material, actually we can consider that as an electron moving in a periodic structure, like here. So therefore, the purpose for these studies, we want to understand the electron movement with considering the different cases, different potential here. So therefore, there could be the three different cases that electron movement inside this potential, which can be the first one, the electrons in the free space. And the second one can be the electrons in the deeper of this potential well, or electrons is a little bit in the surface, not really deep, it's in the surface of the potential well here. So that can be considered the three cases that overall to describe that all the electrons' behavior inside this periodic potential. So therefore, the first one, the first issues, the first question we need to address is that the electrons in the free space. So now we can reconsider this as shown me here. We have the E here, and then as usual, we normally have this potential, periodic potential here. And to consider the electron in the free space, so we can make the assumption where to consider the electron in the free space, we can consider as an assumption that all this periodic potential is equal to 0. So if this potential is equal to 0, that means our electron is moving in the free space. So we have electrons can moving in these directions. Electron can be moving in these directions. And also we have the electrons can be moved in these directions. So that's the first case. So with considering electron in the free potential, so we can assume this potential is equal to 0. And next one is electrons will moving inside this infinite potential well, which is here. This is considered that the electrons is moving, but now is moving in the place where has a infinite potential well. So in this case, we consider this one. This is a x equal to 0. This is x equal to a here. So now we have several different regions. First, our potential wells should be look like in this way. And then we can divide by several different regions, which is region 1, region 2, and region 3. And now we consider the electrons moving in region 3, in region 2. But since this is a potential well will approach to the infinite, so therefore we can consider this one will be approached to, as shown here. So that's a assumption we can make for the region 1 and region 3, that we can consider the potential will be approached to the as large as possible, and that will be considered as a case in here. And then the next question that we want to deal with is consider the case 3. So in the case 3 is actually as a step potential function. Therefore, we consider this one is a potential. This is not this one. So we consider this one, and then in this space that we have this step potential function. Where this is V. And then we can divide this by region 1, region 2. And now we consider that this is a case where we have the electrons moving toward to the right, face this step potential function. And then the last one is a final one that we want to address. It's actually very realistic for the case that we will face in the semiconductor, which considers a potential barrier. Because if you try to consider this region, if the electron want to move from here to here, actually the potential where the electron will meet is shown roughly like this one. Then the last case that we are interested in to solve, which is considered still the same. We are in the x equal to 0, x equal to a, and there is a potential barrier. There's a potential barrier here. And in here, we can divide also by the 3 regions. Region 1, region 2, and region 3. And now we consider V0 for this potential barrier. But now the electrons moving toward the right. But the electron has an energy smaller than V0. So that would be the final case we want to solve. So I hope you can. We don't haven't used any equation to solve and derive something yet. But I want to give everyone a big picture that how this scenario from 1 to 4, step by step, into the case that the case we are interested in, especially the last case, because the last case is exactly the case that we will try to understand when we have the inside the MOSFET, there's a dielectric, there's a gate, and this is exactly the same case where we apply VG, and then we will extract the electrons. We will have the electron accumulating in the channel, but then the electron will be attracted toward the top. So the electrons standing from the viewpoint from electron and versus this barrier, which will be exactly the same, like this kind of a scenario. So that's why I say the last one is a realistic case that is very similar to the typical semiconductor device that we will face. So to further understand, we need to understand the last case, the last case where we have the potential barrier. For sure that we need to step by step from the beginning. The first one, we need to understand what would be if the potential is equal to 0 and the electron moving in the free space, and what would be the equation look like. And then what would be the case that the electron placed in a certain potential well and trapped there, and what would be the equation look like, what would be the electron behavior looks like. And then the third one would be, how about if the electron is faced a one-state potential function, and then what would be the electrons, what would be the equation, what would be the electron behavior. And in the end, the last one, we just combine what we know from the 1 to 3, and then therefore we can get the result from the last case, which is realistic in the typical MOSFET we will face. Okay, so these 4 are the general questions we need to solve in this chapter. And by solving these 4 equations, we can finally understand how electron can be moved in a certain semiconductor material. And therefore, we start to use something very complicated equation. The one that is very famous is the one we call this Schrödinger's equation. And the first one we consider is a time-independent equation. So the first one, we have this general one-dimensional Schrödinger's wave equation as shown in here. So I won't show again how this equation coming from. I believe you can find a lot of basic material. I just apply. So as I say that we are a semiconductor engineer, we mainly try to use some fundamental knowledge, apply this fundamental knowledge to analyze the case. So to understand the fundamental equation, I for sure that you can find lots of material. But in here, we mainly in the application aspect. So we try to apply this wave equation, whether in the beginning, this one is showing here. the phi xt. The phi xt is a wave function, but has a two dependent variable, which we have the x and t. So that means the wave function right now, this is a very general wave function that's dependent on our space, x, and dependent on our time here. But the first, since we want to simplify, this wave equation become as a time-independent wave equation. So now we can assume the wave function can be written in the form. This is a phi xt is equal to this one. Where phi x now is only the position x, only wave function, and phi t now is only the time-dependent only wave function. So this is a very general mathematics that we can divide these two parameters as each parameter times together. This is what we learned from the engineering mathematics. I believe that everyone here who have already learned the engineering mathematics, and this is one trick we learned from that. So we apply this trick and put again inside this wave equation. So now you put here inside this with a certain derive, and also we consider now the phi t can be considered as a form, as an exponential minus j, certain number times t, and therefore this phi t will be equal to this one, exponential minus j omega t here. So we put this phi t in this wave equation. In the end, we can get this one is in the end become E. So finally, we can simplify the wave equation that depend on the two parameters. Right now it's become time independent. So now we have this wave equation is only x space with only the space variable. So it's only space dependent. So now we can have the time independent. So for sure, I fully understand that this calculation sometimes looks scary, but just try to remind that remember our goal. So this fundamental equation is not trying to complicate the Earth. Actually, just want to support our physics understanding. So the goal for this equation in the end is always will be transformed in the very simple consideration in the simple form that's based on the certain assumption, and then this in the end this derived equation will just the goal is try to support our physics-based understanding. So it's getting more important to understand what the physics behind for this equation rather than try to calculate this equation. You can calculate once, but I think once per your life probably is enough, but it's important to understand the physics behind. So now we have the phi xt, right? That's how we described in the previous slide, but we have to talk a little bit more about what is the physical meaning of the wave function. So this phi ft wave function, the purpose to this wave function is to describe the behaviors behaviors of an electron in the crystal. I know the wave function, it's this kind of name is not very straightforward, especially if you consider the Mandarin translation. When we have the high school, we learn the modern physics. We always, in high school in Taiwan, we only have this Mandarin textbook. We only call this as a 波函数. Of course, the wave function doesn't sound like a name that's very straightforward to understand. But in here, the definition is pretty simple. Just try to have this function in the end to describe the electron behavior in the crystal. And therefore, if we consider this phi xt, where we apply the previous mathematical tricks that we consider as I think this is how we call the separation variable. This, I guess this, as I remember correctly, this is a method we learned from engineering mathematics. We call the separation variable. So we consider this equation can be calculated by this. And furthermore, the phi x and also the phi t can be expressed by exponential minus j e over h bar t. And therefore, we just apply what we have from last slide. So we have an exponential minus j omega t here. So now we do the one trick. We consider this square, which is equal to this times this. And once we put it as a 1 star, that means that we change this sign from negative to the positive we have here. So we put this one times this together, which will be equal to this one. And then we have this will be eliminated, right? So then, therefore, again, we found out that with this wave equation that has a x and t dependency, in the end, it's become the wave equation only has a x dependency, because now it's reduced to x dependent only. So therefore, this wave equation with xt squared in the end can be simplified as here. And of course, this equation is still a little bit vague. It's difficult to understand, but the meaning of these ones become this result indicates the probability density function, and then is independent of the time. So the most important information is that now we try to understand the wave equation, but then in the end lead to the conclusion that this is related to our probability. And then also it's independent of the time, and then it's only location dependent. So that means based on the wave equation, what we derive from the wave equation to the quantum mechanics, in the end that will tell us once you have the electrons, you have the barriers here, and you have the electrons trying to move from left to the right. And then, as I already tell you, the answer is that we will start to see the electron penetrating and tunneling in the other side. So therefore, based on the quantum mechanics, we can have a chance to see the electrons on the other side. But how do we estimate this electron can be only considered as a probability. So that means once we have an electron jump over the barrier, that's what we call the tunneling, reach to the other side, the only chance we cannot accurately determine how many electrons here. We can only have the probability to describe this behavior. And also, it's only the location dependent only. So that's a very important meaning coming from wave equation. So what we derive here just suggests that once you have the bunch of the electrons injected toward the barrier and tunneling to the other side, we cannot accurately determine how many electrons can be tunneled and where are they. What we can do is only for the probabilities is something we know. So we can only estimate the probability for this electron tunneling. So that's a main, very important meaning coming from the wave equation. And then this will lead into the later has a great impact on our analysis for this tunneling mechanism. So the short summary is shown here. So in the 1926, Schrödinger provides the formation for formula, provides this formula called wave mechanics, and that's combined several different principles where we already discussed the principle for quantum wave particle, and then particles follow the laws of conservation energy. In the end, the wave function can be expressed as shown here. And therefore, we put this one in the time-independent Schrödinger's wave equation. So we got this conclusion. So this conclusion, this output equation shown here is indicate that the wave function is a probability density function and is independent of the time. So these results lead to the major difference between the classical and quantum mechanics, because in the classical mechanics, we can determine the position of a particle or body precisely. So in the classical physics, in the Newton physics, we are able to estimate everyone's position very precisely. But however, in the quantum mechanics, the position of a particle can be estimated only in terms of a probability. So this is one of the very important conclusions so far we learned from the wave equation. So this gives us the idea that once you have the electron moving in the certain semiconductor material, what we can only estimate the position will be only consider their probability rather than precise determine the location. Okay, so I think we will stop here because from the next slide we will start to apply application of this wave equation to start to solve the previous cases we will face. So we'll stop here and then see you everyone next week.